Hello, welcome to my talk on what are the streamline, pathline, and streakline of fluid motion. In this talk, I will make an introduction of the definitions of streamline, pathline, and streakline for fluid motion. And then I will use an example to illustrate what is the streamline, pathline, and streakline. And then I will discuss the equations for streamline and pathline. Then an example to show the streamline and pathline are same in a steady flow. And last, a summary will be made for the streamline, pathline, and streakline. For fluid motion, we need some way to illustrate how the fluid particles move around in the fluid domain. But how? Basically, we have three different ways to describe the fluid motion. The first one is the streamline, based on the reference. A streamline is a continuous line within a fluid, such that the tangent at each point is the direction of the velocity vector at that point. A pathline, or the particle trajectory, is the trajectory of an individual element of fluid. A streakline is the locus of all fluid elements that have previously passed through a given point. From these definitions, it's still quite difficult to understand what are the streamline, pathline, and streakline, or what are the difference among the streamline, pathline, and streakline. In this talk, I will use the example, a steady flow around airfoil, to show what are streamline, pathline, and streakline, and what are the differences. A streamline is a continuous line on which the velocity vectors are tangent to the line at every point. If we take a snapshot of the fluid pattern, we can see the instant streamlines, the grid lines on which the velocity are all tangent to the lines. For instance, the streamline, the dashed black line, and we have many points on the line, P1, P2, P3, P4, P5, and P6. And on each point, the velocity vector V1, V2, V3, V4, V5, and V6 would be all tangent to the line at each point. A streamline is a mathematical curve which can be solved from the streamline equation. I will talk this streamline equation later. And the dynamics for streamlines is not direct. It is through the observed velocity field. We will see this later. A pathline is the trajectory of a fluid element, a line the fluid particles travels in the time history. So if we look at the one fluid particle, the red square, which moving in the fluid, so at time t1, the fluid particle moved to here, and at time t2, the particle moved to here. So the pathline is this dashed black line. And the next time step, we have the time t3, and the pathline at this. At t4, the pathline is this, and T5, the pathline would be given as this. T6, and T7. Principally, the trajectory of a fluid particle can be solved from the dynamic equation in Lagrangian approach. We will see this later in this talk. However, in reality, the pathline can be more likely obtained by integrating the velocity field, which is actually solved in the Eulerian approach. So, the pathline, the vector s, would be given as the integral of the velocity to the time given as this. A streakline is a line linking all fluid elements that have previously passed through a given point. So a streakline is actually a string of fluid particles that pass a given point. For instance, here P. At time t1, the fluid particle moves to here, and at time t2, the first particle moved to here, and the second particle would move to here. And at time t3, the first particle is here, the second particle is here, and the third particle is here. So we can see this dashed line is the streakline. And at t4, so the first particle moved to here, and we can see the streakline link all the particles together. At time t5, we have this, and we can see at time t5 we have particle 1, particle 2, particle 3, particle 4, and particle 5. So the streakline links all the fluid particles past the same position and make a string of the fluid particles, see here. In a steady flow, the streakline has the same meaning as the pathline. In reality, we can see the streakline in the fluid visualization, a dye in a water flow, or a smoke in an airflow. See the picture here. This is the smoke emitted from the chimney. We can see the flow is turbulent, and the streakline would be very complicated. However, if we draw an average streakline, it would be something like this. In this slide, we will see in a steady flow, the streakline, pathline, and the streakline would be all coincident. See these gray lines in the steady flow path and airfoil. If we take a snapshot of the flow at any time, for a steady flow, the pictures would be always the same. Therefore, the streamline would be same all the time. In this regard, in the steady flow, the streamline and the pathline have same concept in principle. So is the streakline. The velocity at any point on the streamline or the pathline are tangent to the lines based on the definition or the dynamics of the lines. And in a steady flow, all these three lines are time invariant, thus all three lines would be coincident. Now in the next few slides, we will look at the dynamic equation or the mathematical equation for pathline and streamline. For the pathline, we have the dynamic equation for the fluid particle. Suppose if a force acting on the fluid particle is the vector F, then the dynamic equation of the fluid particle would be given as this. Here m is the fluid particle mass, and s is the vector for the pathline. This dynamic equation can be written as the component for the coordinate x, y, and z. Here, fx is defined as capital Fx divided by m, and fy equaling to capital Fy divided by m, and the same for fz. All these are the force component per unit mass. So principally, if we solve the dynamic equation, we can obtain the fluid pathline or the trajectory given by the vector s or by the component x, y, and z. So if we obtain the vector s, then we can draw out the pathline as this. For the streamline, the basic equation is given as d vector s cross timing vector v equaling to 0. Here, the dashed black line is the streamline, and the red dot is the point on the streamline. So we can see the velocity is tangent to the streamline, and so is ds. So the physical meaning of the streamline equation is that the increment delta vector s on the streamline and the corresponding velocity vector are both tangent to the streamline at this point. So in calculation of this cross product, we have the expression given as this. The first row, vector I, vector j, and vector k are the unit vector along x-axis, y-axis, and z-axis respectively. And the dx, dy, dz in the second row is the component of the vector ds. And the third row, u, v, w, are the component of the velocity vector v along the three coordinates in here. So when we calculate this would be given as this. In calculation, we look at the determinant, and if we want to calculate the component on x-axis, that means the unit vector I. So we can cross the row as this and the column corresponding to I. So we have a smaller determinant than this. The value in the brackets would be calculated. The orthogonal term together, w dy minus v dz. And here we notice the unit vector I is positive. And for the calculation for the unit vector j, the component would be calculated as this. We cross the first row and the second column. So we have 4 components in the determinant. And then we can calculate the value, use the orthogonal w dx times together minus u times dz. However, in this case, we must take the value on the unit vector j be minus. So we have the result as this. And for the component on the unit vector k, we can calculate as this way. Here we have the positive k, thus we have the result as this. Based on the streamline equation, it is required this equation. And to make the equation to be 0, that means all the components respectively on x-axis, y-axis, and the z-axis would be all 0. So we have the equations as this. And we can write these equations in different format. So the first equation would be expressed as dz divided by w equaling to dy divided by v, and so on. From these three equations, we can obtain the equation as this. So the increment on different axes divided by the corresponding velocity would be same. This actually is the constant dt, since we can obtain this from the increment dx calculated by u dt and dy calculated as v times dt and dz as w times dt. So we have the expression as this. We can see in physics the streamline has the same meaning as the increment on different axes calculated as the corresponding velocity component time step dt. So this physical meaning is very clear as we can understand. Now we look at an example for the dynamics and motion for pathline and streamline. The example is a ball moves on a horizontal surface at a speed v0, and then the ball freely falls after leaving the surface. See the drawing here. The dynamic equation can be easily built as this. And we can also give the initial condition at t0, x, y, and z are all 0, and the velocity at t0, vx equaling to v0, and vy and vz at t equaling to 0 are both 0. So the solution of this ball motion can be easily given as this. Now in this slide, we will see how the ball pathline is calculated. From the solution of the ball motion given as this, we can calculate time t given as x divided by v0. And then we can substitute t into the third equation. So we can obtain the relation between z and x given as this. This is the equation for the pathline of the ball motion. And if we draw this in this coordinate, we have the trajectory as this. And then we can use the same example for studying the streamline. And we have obtained the trajectory of the particle is given as this. So we can calculate the velocity component u given as this. V is 0 and w is given as this. And again, we can obtain the time t from the first equation and put these two together. So we have the velocity component in terms of the coordinates rather than the time. So we have the expression for u equaling to v0, v equaling to 0, and w given as this. Now we can use the streamline equation as we have shown before. So this dx over u equaling to dz over w. So we substitute the velocity component into the streamline equation. We have the expression as this. And this can be written as this. So integrate this differential equation. We have the equation for the streamline as z equaling to this. Here, the initial condition is applied when t equaling to 0, x and z are both 0. So if we compare this streamline function to the pathline function, we obtained in the previous slide, we can see the streamline function and the pathline function are exactly the same. So we draw the streamline, we have the line as this. So here we can see the ball motion is very similar to the fluid motion in a steady flow. So in this case, the pathline and the streamline would be same. And another question for this example is, because we consider the falling ball, so the force is only the body force, the gravitational force acting on the ball. There is no surface force acting on the ball. This would be very different from the actual fluid particles, which is subject to the surface force due to the pressure and due to the viscosity of the fluid. In that case, the dynamic equation for the pathline in Lagrangian approach would be very difficult. We will see this in the future talk on this topic. In the last slide, a discussion would be made for the pathline and the streamline. For the simple example of a free-falling ball, the pathline and the streamline are same. We solve from the dynamic equation and from the streamline equation. Because this falling ball is very similar to a steady flow, and we know for a steady flow, the pathline and the streamline would be same. So it's the streakline. In fluid dynamics, the problem could be much more complicated. Generally, we cannot solve the motion of the fluid particles in 3D viscous flow directly in Lagrangian approach because the difficulties in calculating the surface force due to the pressure and due to the fluid viscosity. The conventional method for getting the pathline and the streamline is from the fluid field, which is solved in Eulerian approach. If we know the fluid field, then we can integrate the velocity field to obtain the pathline. While for the streamline, we can simply solve the streamline equation to obtain the streamlines. In steady flows, the fluid pathline, streamline, and streakline are all constant, but they should be different in the unsteady flows because the time dependency for the streamline, pathline, and streakline